These are the notes for LT1 in the thermodynamics unit. So the target says that I can apply the kinetic theory of matter to the 4 states or the 4 phases of matter. You could say that either way. Obviously we'll get to this idea of what kinetic theory is, but the word kinetic should make us think of something just from our energy unit that we just finished. Remember, if something has kinetic energy, it's moving. So this must have something to do with movement. And then if it's a kinetic theory of matter, the first task might be to define matter. And if you Google matter, one of the things it'll say is anything that has mass and takes up space. Well, that almost takes you to another Googling of what is mass. So think of it this way. We probably all know what an atom is from middle school. Okay, and we talked about atoms. You probably did a project where you had to model an atom somehow. So you could build it, you could draw it, but you got into the idea of the fact that atoms bond together. Right? For right now, we'll just say they join together. So atoms join together to make molecules. So one molecule that every one of us has to have is water. And to me, water always reminds me, at least our model of it, of Mickey Mouse. Because water is H2O, which means there's 2 hydrogens and 1 oxygen. And hydrogens are smaller than oxygen, so I always think they look like the mouse ears when they are bonded on there. But this would be a molecule of water. And then what could happen is other water molecules may stick to this one. So maybe if we did another little mouse ear coming here, here's an oxygen, here's a hydrogen. So think about a glass of water. It's going to have lots of these kind of packed on top of each other and bound together. Okay, so matter is just anything where you've got at least one atom, and atoms usually aren't found alone. They're usually bonded with other atoms, so we call it a molecule. So let's just get into this kinetic theory of matter. So kinetic theory of matter. It has 3 major kind of principles within it. And the first one is that molecules, so it could be like this, a molecule of water, are in constant motion. Okay, so anywhere you can look, touch right now, there's molecules going like crazy. So molecules are in constant motion. Okay, they don't stop. The only way they stop is if we can take something down to absolute zero. And there is nothing that you are in immediate contact with in your life that is in absolute zero. That's in some weird lab setting somewhere. Okay, so molecules are in constant motion. They're zigging, they're zagging. And when I say zig and zag, that motion is random. They don't get together and coordinate and say, okay, everybody, let's go left. Okay, everybody, now let's go right. And let's go up and let's go down. They just go crazy. It's probably like a kindergarten classroom the first week of school. I find those little buggers terrifying, but I gotta believe that it is crazy the first week of school. Those kids don't know how to follow directions and all do the same thing. That's how these molecules act. Okay, so they're jiggling around and they're jiggling every which way. And what happens is if you raise the temperature of those molecules, you cause them to go even crazier. They will have more motion. And we do a PhET simulation in class and it's on Moodle for LT1, where you see that. If you have this beaker, okay, so we're going to have a beaker here, and we're going to put some fire under it. And you guys know I'm not very good at drawing fire, so we've got a flame under that beaker. When these things are evaporating, when you go from, let's say, maybe this is liquid, to where there's a little space, okay, so maybe this is our liquid phase, they're zigging and zagging pretty good. When you're solid water, when you're ice, okay, they're packed right in here, and they're going to get very little motion there. They're just going to kind of jiggle in place. Anything that's a solid, like your table, they're jiggling, but it's almost like back and forth. They don't actually travel. But when you get, so this is an S for solid. When you get to a gas form, notice the molecule size doesn't change, but the spacing does. When they're a gas, you've got crazy fast motion. When it's a solid, you've got slow motion. All right? And if we could take this down to absolute zero, then we would have no motion at all. So, kinetic theory is pretty simple. Just think, all right, everything's moving, it's moving randomly, and the higher the temperature of the molecule, the faster they're going. All right, so very, very simple stuff. Now, within this unit, or within this target, I should say, we're going to deal with the phases of matter. And we've already kind of touched on it here. But we'll start with the idea that there's 4 of them, which is a little different because in everyday life, we think of 3, solid, liquid, gas. We've thought of that since we were small. So we'll start with the solid. And one of the things that we have to get used to is this idea of interparticle forces. Inter means between. So you think about if you interrupt somebody, you come between their conversation or whatever they were doing. You stop them and then the task that they were focused on. So inter means come between. So interparticle forces, and I don't see a reason to write that out a lot. So the standard abbreviation for those are IPFs. They are the strongest here. So if you've got a solid carbon, let's say, because lots more things than just water was going to have 3 phases. So if you've got a solid chunk of lead or carbon, whatever, it doesn't want to let each other go. Okay, each particle wants to hang on tight. It's like when you're a little kid and you play Red Rover, and you don't want to pick the 2 big kids to run through that have a really strong grip, right? Those people with a really strong grip, a really strong hold on each other, they have what would be called a fixed shape. They don't want to bend. So we say that solids have a fixed or what is called a definite shape. Your table isn't all fluid and like oozing right now. Your table is a fixed shape. If you want to break it, it's going to take a lot of force to break the interparticle forces. Those molecules are hanging on to each other. So they have a fixed or a definite shape and a fixed volume. So volume, remember, is how much space you take up. So think space, space occupied. There we go. Trying to figure out how to say that. So how much space you take up. You're not going to change the volume of a solid very easy. So unless we change its phase, and that's not what we're doing right now. So solids, same shape, same volume. But if we increase the temperature of something and we go to a liquid, so now we're in a liquid state, the IPFs are weaker. So the interparticle forces are weaker. Again, playing Red Rover, you try to get through the line, and there's some resistance there, still resistance, but not as much as the solid. So these things will have an indefinite shape. That means it will change. If you've got a can of pop, think of your favorite pop, maybe it's a Pepsi, and you open that can up, it's 12 ounces, that's a can of pop. If you pour that into a big tall glass, you still have 12 ounces. If you dump it on the floor, you still have 12 ounces, but it will take up the shape of whatever it's in. So that's what the indefinite shape means. Yet we kept talking about the 12 ounces because that part doesn't change. So the shape will take on whatever it's in. You can pour it into any fancy glass you want, but you will still have 12 ounces of pop. All right, that's essentially the definition of a liquid. So that takes us to the next one. So we're increasing temperature as we go down this list. A gas. These are the weakest IPF forces. So there's still an attraction between molecules, but they are very weak. So I'm going to put it down here so we have a little bit of space. So this one is an indefinite volume. If we open the door to the classroom, gases will come in and gases will go out. There is no fixed volume. They will change. So indefinite volume and an indefinite shape. So open the window, gases come in. Open the window, gases go out. Okay. These forces are so weak that Yeah, there's a little attraction, but they don't like each other that much anymore. Okay, they're kind of over it. And that gets us into this fourth phase, which we watched a little video also on Moodle regarding the fourth phase of matter, which is plasma. Now, what plasma is not? It is not going up to BioLife and donating your plasma. That is a different type. Okay? What happens with plasma is it is so hot. All right, so the temperature is so high that the matter becomes ions. And that's kind of fancy. That becomes ions. Because what happens with an ion, all right, go back to review of an atom. Every atom has a positive nucleus because there's protons in there. And typically, it has some electrons cruising around it. We say they orbit around it. Well, what happens when they become ions is the electrons are stripped away. Like, it's so hot that these electrons are pulled away from this nucleus. So they take off. And these streaming ions are the number one phase of matter in the universe. So think about what there is more of than anything else in this universe. We're not talking Earth. Okay, universe. Think stars. Okay, stars are just essentially big balls of ions, big balls of plasma. A plasma TV. That was kind of the up-and-coming thing for a while there, and now they've been phased out with the LCD, LED stuff. But if you have heard of a plasma TV or you have a TV, that was the idea with that as well. But we're primarily concerned about stars. You could argue that a bonfire has plasma in it, okay, because there's parts of a bonfire that are that hot where within the oxygen, the whatever that's being burnt, the carbon, electrons are being stripped away there too. When you start to get to the blue flame, then that's the crazy hot stuff. All right, so plasma is actually the number one phase. So, and the most common is just that on Earth we don't see it as much, which is why people focus more on solids, liquids, gases. All right, so solid, not moving very much, think fixed everything, doesn't want to change. By the time you get to plasma, there are no inner particle forces. Okay, it's over. They have broken up. All right, there's been so much energy added to this phase that the ions, the electrons are ripped away, and you've just got streaming balls of gas. And that is target 1.